Hi there, it's Jason Gorman from Codemanship with a video about modular design principles in Java. This is following on from the previous video that I recorded about the principles of simple design. If you recall those, we should make sure that our code works, that it's easy to understand, that it's low in duplication, and that it's the simplest thing we could have done to pass our tests. Moving on from that, we also need to think about how our software is composed in terms of modules. So in this video, we're going to be demonstrating the principles of modular design. But let's quickly go through them before we look at an example. First of all, we should aim to have our modules each do one job, to have a single responsibility. There's two reasons for this. One is so that when we make a change, we know we're only changing one part of the software and we're not changing a module that's doing multiple things, thus risking the possibility that we break code that's got nothing to do with the code that we're changing. But also because when we compose our software out of pieces that only do one job, we get far more choices about how those pieces can be combined, can be composed, if you like, to do new jobs. One of the best examples of that is Unix pipes. So with Unix pipes, we have a whole set of programs, each of which does one job, like reversing a string or converting a string to lowercase, etc. And we can chain those programs together to do much more sophisticated things. And because each program does one job, we get a lot of choices about how we can chain them, essentially infinite choices about how they can be chained together, how they can be composed to do new things. So for that reason, we should aim to have modules that only do one job, that have a single responsibility or a single reason to change. So that's very important. The next thing we need to think about is what these modules know about each other, and as much as possible we want them to encapsulate their internal workings, to hide the inner detail, if you like. And we'll talk about a style of design here called tell, don't ask, where rather than having modules that do calculations and other modules that hold data, so the modules doing the calculations, the modules doing the work, if you like, have to ask for the data from these other data modules. Instead, they tell the objects that have the data to do the work themselves. So those modules hide the data, they hide their inner workings, and other modules can just tell them to do their jobs. So we'll talk about tell, don't ask in that style of design. Also, modules need to have swappable dependencies. So what we do is we compose modules out of the modules that they tell to do the other jobs, by passing them in from the outside using dependency injection wherever possible. And that allows us to swap those implementations, the implementations of those modules. So for example, we can swap an Oracle database with a NoSQL database without having to rewrite our client code, our core business logic. And it also means, of course, that we can stub and mock those dependencies in our tests. So all sorts of ways that we can flex our design, if you like. We can change our design without having to rewrite the client code. And these are like the three pillars of modular design. Each module only does one job. Each module hides its inner workings so that other modules know as little as possible about them. Just tell them to do their jobs, basically, and they don't need to know the details. And then finally, these modules, when they talk to each other, those dependencies should be swappable, usually by dependency injection, so that we can replace an implementation of one module with an implementation of another module that looks the same from the outside, so that we don't have to rewrite client code. And that's kind of the whole goal of good modular design. It's to enable us to localize as much as possible the impact of making changes to a single module, so that the rest of the code is unaffected. And that reduces the cost of making changes to our software. So it's very, very important. Now, there's one final principle that is language specific. Some languages that have static typing and enforce binary compatibility of interfaces, for example, Java and C# and C++, we also have to think about what else those modules are exposing in terms of their interfaces, because as we'll see with a little example, if a module is exposed to features they're not using, in other words, they're binding to an interface that includes features they don't use, then when we change those features, even though they're not using them, that client module would then need to be recompiled, retested, and redeployed. So we need to think about how client-specific our interfaces are. Do they include things that the client doesn't need to know about? And if so, maybe we should introduce a client-specific interface. So we'll take a look at an example of that as well. So 4 things to look at. Let's see some example code. That's always where the rubber meets the road. So I've got this carpet quote class here. And what it does is, given the length and width of a room and the price per square meter of a carpet and a policy on whether we need to round our fitted cost to the nearest square meter of carpet, we calculate a quote essentially for that carpet fitted in that room. Now you can see from the parameters there and from the code inside the calculate method that carpet quote is doing all of the work here. Now this code ticks all the boxes of simple design. First of all, it works. Let's just prove that. Let's run the tests and see. So that's the most important design box ticked. It does work. It calculates the prices correctly. Now, is it easy to understand? Well, I think it is. I think it's pretty obvious what's going on here. So this code does clearly communicate its intent. So that's the second principle of simple design. Can I see any duplication? Well, not that I would worry about. So we're ticking the third box there. It doesn't repeat itself. And then finally, is this really the simplest thing I could have done? Well, it probably is. I think it probably is. So it's ticking all the boxes of simple design, but that doesn't mean that this design doesn't have potential problems when it comes to changing the code as we move forward. So let's go through our principles of modular design. Principle number 1, module should do one job, or have one reason to change. Now I can imagine wanting to change how the area of the room that our carpet is going to be fitted in. I can imagine wanting to change how that's calculated without changing how the price of the carpet is calculated. So I can imagine wanting to change this line of code and these lines of code independently of each other. I think they're 2 different things. So maybe these belong in their own modules. So let's refactor that and see what it looks like. I'm going to start by extracting length times width into its own little method there, and let's call that area. Not keen on the word get. We'll talk about gets later. So let's extract a method for that. Don't need to do any of that, thank you. And let's just rerun our test, so keep it working. Okay, now we can do a similar thing with that method there. So first step is get them on their own. So that's the fitted price. Okay, so step number 1, get them in their own methods. Okay, now that I look at these methods, and this is very often how I will discover objects in my code when I'm refactoring and the design is evolving. When I look, for example, at the FittedPrice method and at the area method, I'm seeing an object here. Area of what? Well, area of something that has a length and a width. So I'm seeing a potential object identity here. So let's see if we can tease out this type of object. Let's introduce a parameter object that has length and width as fields. It's the length and width of a room. Okay, let's see how that looks. And what it's going to do is it's going to create a new class, and it's create an instance of that class, and it will have length and width fields, and those will be set in the constructor, hopefully. Okay, and off it goes. So now you can see up here, the area method is using this new room class, and if we look down here, we can see that it does indeed use the fields of room. Now this method area is displaying what we call FeatureEnv. FeatureEnv is a code smell. You can read about it in Martin Fowler's Refactoring book, where essentially a method of one class has an unhealthy fascination with envy for features of another class. In this case, it's got envy for the features of room, giving a strong indication that this method is in the wrong class. So let's move it to room. Okay. There you'll see now it's a method of room. Let's rerun our tests. So now room is doing the work, and all carpet quote has to do is to tell room to do that work. Similarly with FittedPrice, I think there is an object hiding in there that has a price per square meter and a policy on whether we round up our price to the nearest square meter. So similar kind of deal here. Let's introduce a parameter object and see if we can tease this object out. I don't think it has an area. I think that will be a parameter of this method still, but I think it has a price per square meter and whether we round it up. So let's give it a name. That is the carpet. It's the price of the carpet. Okay. Let's refactor that. So now the FittedPrice method is using carpet, and as you can see, it has FeatureEnv for carpet. So let's move it to the object of its FeatureEnv, which is carpet. There we go. So now carpet is doing its work with its data, and room is doing its work with its data. Let's take a look at carpet quote now. Interesting, isn't it? It doesn't do any of the work anymore. Doesn't do any of the work anymore. So we're telling room to calculate the area, and we're telling carpet to calculate the fitted price. Tell, don't ask. So rather than asking for the data and doing it itself, it's telling these objects to do that work with their own data. So we're ticking two boxes now, which is we're telling, not asking, and room does one job and carpet does another job. So each module has a single responsibility. We take a look inside room. These accessors get price per square meter, is round up to square meter. Do we need these anymore? Do we need to expose our internal data? I don't think we do. So I'm going to inline these, get rid of them. Let's just do them both. I think it's fairly safe to do them both. And then let's run our tests. So now carpet calculates the fitted price without exposing any of the details about how it's doing that. We also take a look at room. It's a similar kind of deal. Room doesn't need anyone else to know that it has a length and a width. It just needs people to know that they can tell it to calculate its own area. And as we'll see moving forward, that's going to introduce a lot of flexibility into our design later. So each module is doing one job. They're telling, not asking. Carpet quote is telling room and carpet to do their jobs. What else can we improve about this? Well, it still knows about the length and the width. That's the problem here. In other words, it's binding directly to the implementation of room. So it knows that it's this implementation. So if we wanted to introduce, for example, a circular room or some other kind of room with different dimensions, we would have to rewrite carpet quote to do that. And our goal here with modular design is to design things, is to compose our modules in such a way that we can change their dependencies without having to rewrite the client module. So this is where we get to our third principle of modular design, that dependencies should be swappable, ideally by dependency injection. So what I'm going to do is I'm going to have this injected as a parameter. So let's introduce a parameter called room. There we go. And now that object is being created in our client code. In this case, it's being created in the tests. And it's being passed in, it's being injected from the outside. There it is there. So carpet quote just knows that it's a room and you can tell it to calculate an area. It doesn't know that it's got a length and a width. Similarly with our carpet, we could inject this. Let's introduce a parameter for that. Super duper. So now, we've got carpet quote doesn't know anything about the dimensions of room. It doesn't know anything about the pricing fields that are associated with pricing a carpet in a particular room. All it knows is it can tell a room to calculate an area, and it can tell a carpet to calculate a fitted price. Now let's finish this off. We can inline that. We don't need a local variable for area anymore. So now carpet quote is essentially a composed object. All it's doing is it's telling other objects to do the work. It's coordinating the work, if you like. And it knows very little about the carpet. It knows very little about the room, a lot less than it did know. And if we wanted to, we could extend room or we could extend carpet and pass in other implementations. For example, using Mockito, I could create a mock room or a mock carpet and pass those in, and carpet quote would be completely unaffected. Now, if we wanted to complete this refactoring, I think because I would be relying on implementation inheritance if I wanted to extend room, and I'm not a big fan of that, I think I'm going to tie a little bow on this. what I'm going to do is I'm going to first of all be a bit more specific about the name of room here. So let's rename this to a rectangular room, one that has a width and a length. Okay. And then what I'm going to do is, to make the dependency totally swappable, is I'm going to make this completely abstract. I'm going to introduce, I'm going to extract an interface here. And we can call that just room. Got you, Jason. That needs to be public if you want to have it on an interface. So let's do that. Thank you. Now let's extract an interface called room. And the idea is that we can have all kinds of rooms. We can have rectangular rooms, we can have triangular rooms, we can have circular rooms, we can have L-shaped rooms. And importantly, none of that will affect the code inside Carpet Quote. It doesn't need to change. Okay, it's going to analyze the code to look for references to rectangular rooms, see if it can swap it with room. There we go. So now Carpet Quote only knows about this interface room. So we have total swappability now. Total swappability. And we could do a similar thing with carpet, so that we could maybe have different kinds of pricing policies for different sort of classes of carpet, if you like. So those are our first three principles of modular design, illustrated, I think, by a very simple example, quite neatly, that even though that code is working and it's easy to understand and it's got no duplication and it's as simple as we could probably make it, there are still potential gotchas in the design if we want to vary, for example, how we want to calculate prices independently of how we calculate areas of rooms. So now we have something that's much more modular and much easier to change going forward. There's a lot of flexibility in this design. So those are the first three principles. Each module should do one job. Modules should hide their own working, so when it comes to how modules talk to each other, rather than asking for data, they should tell the object that has the data to do the work. Remember to look out for getters, and in particular look out for that code smell FeatureEnv. Make sure the methods that are doing calculations are in the right classes, and a lot of it is all about putting the responsibilities in the right place. And you'll notice I kind of worked that backwards. I extracted the method and then I introduced the object and then moved for the parameters. So I said, well, here's the method, that's the data that it needs on the most part, and therefore that's an object, if you like, that has that data and does that particular work. So I'm kind of discovering objects backwards here, which is often a much better way of doing it. If you start with the work, figure out what data is required in terms of parameters, and then introduce an object and move that method to that object. Nice little heuristic there for you. And then finally, I'm making my dependencies swappable by dependency injection, and indeed ultimately super swappable by introducing an interface here, so that we can have all kinds of rooms and Carpet Quote is completely unaffected. And that's generally a very, very good sort of practice, that objects should be composed from the outside. Their dependencies, the objects they collaborate with, should be handed to them by the client. And we call this inversion of control, that the actual order of calls in terms of real implementations is decided from above. It's not hard-coded as it was before into our code here. And that, for most languages, for JavaScript, for Ruby, for COBOL, for Fortran, for C and for C++, and for most modern languages, you can achieve all three of those things. You can achieve modules that do one job. You can hide the inner workings of those modules from modules that use them. And in most languages, you can make those dependencies swappable in one way or another, even, as I discovered recently, in COBOL. So most languages, you can achieve this level of modular design. Okay, now, this final part of the video is actually my third take of this, and you'll see why in a minute. But there's one final design principle we need to think about, and to illustrate that, I've got a little separate example here. So this is a different example to the Carpet Quote one. Imagine we have this class book in our library system. You'll see there that it has a title, an author, year published, and information about book ratings. And then it exposes this information in terms of a book summary. There's a method there for rating books and an accessor there for getting the average rating for each book. Now, book stats is a client of the book class, and it's using the getRating method. Library is a client of the book class, and it's using the getSummary method. Now, because we're working in Java and we have binary compatibility of interfaces, essentially what it means is that whenever I make changes to, for example, the rate method or getRating, library is actually affected by that. It needs to be recompiled, retested, and redeployed, because this is a statically typed language with binary compatibility. So we're essentially creating a new version of the interface, and the JVM will know that. Sorry, the compiler will know that. Similarly with book stats, if you make any changes, for example, to getSummary, if we change the signature of that, then book stats needs to be recompiled, retested, and redeployed. So this is language specific. This is not a problem we would have in, say, JavaScript. It's something that we need to think about in languages like Java and C# and C++. So how can we reduce the risk of a client class being affected by changes to features that it's not actually using? Well, what we could do is we could extract client-specific interfaces from book for each of these clients to use. So interfaces that only include the features that BookStats wants to use or that library wants to use. So let's do it for BookStats first. Let's extract an interface just for BookStats to use. Okay, and let's call this rated. Now, what we need to expose is getRating. That's what BookStats is using. Now, people instinctively go, and also rate, because that's obviously to do with ratings. That's not what we're talking about here. It's not about a conceptual grouping of methods based on a particular concept or type. It's about making our interfaces client-specific by only exposing what the client needs to see. Stats is using ratings, it's not creating ratings. So it only needs to be able to get ratings. Now we're going to do this refactoring, and this is why we're on take 3. So what IntelliJ is going to do, usually it's very smart. It's going to say, oh, I can look for usages of book and replace that with rated. But the problem is what it will do is it will try to do that everywhere, including inside library, which I don't want it to do. And then I got into a very fiddly process of trying to exclude all the changes I didn't want it to make. And in the end, I just thought, you know what, it's probably easier to do this by hand. So I'm going to say thanks, but no thanks for that. Let's just run the tests. And what I'm going to do instead, I'm going to go a bit old school here. Let's go into book stats. I'm going to use find and replace. Yep, old school. So I can remember what the shortcut for this is in IntelliJ. Go to find, replace, Control R, yes, of course. So let's match catch whole words book, replace book with rated. And what we're going to do is we're going to do them, let's be cautious here and do them one at a time. So let's replace that one, and that one, and that one, and that one, that one, and that one. And okay, so now they're just referring to rated. Is that going to break our client code? Let's find out. Yeah, I had a feeling it would. So that also needs to be rated. And this method here needs to be rated. So that's our little bit old school, isn't it? There we go. So now we should be able to complete that refactoring and rerun our tests. Goody goody. So now our book stats class only knows about this rated interface. Let's get rid of that for a second. Only knows about this rated interface. It doesn't need to know anything about book. And of course, I would probably go through and rename those as well. So it's only exposed to a simple interface that has a single method for get the rating. So it's not affected by changes to the other methods on book. But by doing this, we've also introduced a little bit of flexibility into our design. I can imagine other kinds of things that might have ratings. Let's do a... No, I'll do that later. I was going to rename all those variables. We'll do that in a bit. So I can imagine wanting, for example, to be able to get stats for rated videos, rated movies, rated CD albums, all kinds of things that might have ratings as well as books. So we've introduced a bit of flexibility as well as making that interface client specific. Similarly, Library's only using get summary, so we can extract an interface for library to use. We could call that, I don't know, summarized. And again, we can probably imagine other things that would have summaries, like movies, for example. Just a string, after all. Okay. And this time I'm going to say yes, because I've already replaced rated, so it's not going to try and replace rated with summarized, hopefully. So this time I will take that help, thank you. And let's rename all of those variables. Off it goes. That looks okay. It's not doing the rateds. All right. And then we immediately rerun our tests. And now hopefully when we look inside the library class, there are only references to the summarized interface. It knows nothing about book, and it knows nothing about ratings. It just knows about things that have summaries, and that's all it needs to know. So it's protected from changes to features that it doesn't need to use. And again, we've introduced some flexibility here. We can imagine other things that have summaries. So there you go. That's client-specific interfaces. The idea basically that if you're working in a language where that matters, like Java or C#, then your classes should present client-specific interfaces, or rather your interfaces should be designed from the client's point of view. And if you watch our video on using mock objects in outside and test-driven design, you'll notice that we end up but with client-specific interfaces because we are designing them from the client's point of view. We're saying these are the methods that this client needs to call to tell this object to do certain things. So mock objects are an interface design tool. They're there to allow us to design interfaces from the client's point of view. So they end up necessarily, by default, client-specific. So there you go. Those are the principles of modular design. Let's look at that slide one last time. So modules should do one job. They should have one responsibility or one reason to change. They should encapsulate their internal workings. They should tell, don't ask when they're telling other objects to do work. Their dependencies should be swappable, usually by dependency injection or something like that, depending on what language mechanism you have, so that we can swap different implementations without having to change the client code. Very important. And finally, in the languages where this matters, interfaces need to be client-specific. It's not something you need to worry about in JavaScript or Python necessarily, but it is something you need to think about in Java and C# and C++. So there you go. Those are the 4 principles of modular design.